Recording started. I think you have all the videos available in both Panopto and YouTube. If you have any question related to that, just let me know. Thank you very much. Just give me 10 seconds. I soften the light in the room, otherwise the screen is not very visible. Okay, perfect. Let's move to the lecture we are studying now. Just wanted to remind you, this is my website, tutorials of sustainable design of water resource systems, and then assessing water resources availability and active methods. And here you can get in the bottom of the lecture the PowerPoint. We are talking about the flow duration curve. Now I switch to the PowerPoint, and we were more or less here. And now let me just check if the blackboard is visible. Yes, it is. Very good. I want to draw a sketch on the blackboard. So 1 second, because I didn't share the screen. So I didn't share the screen. So for those who are connected remotely, we are in this lecture here, assessing water resources availability and active methods. And precisely we are at the estimation of the flow duration curve. We discussed what is a flow duration curve. Now I move to the PowerPoint presentation again. And here is the picture I was talking about. Now let me share the screen because I want to show one thing, make a sketch on the blackboard. So we discussed about the flow duration curve, and last time I already made a sketch on the blackboard of a possible shape of it. And I said that in the flow duration curve we have duration in the horizontal axis and the river flow in the vertical axis. Duration, I said, is expressed in percentage term because it's the fraction of time during which, fraction with respect to the whole observation period, we said it may be 10 years, fraction of time during which a given river flow is equaled or exceeded, okay? So it is usually expressed in percentage terms, but we already discussed the fact that you may find also a different format for duration in the horizontal axis. Precisely, you may find the duration expressed in for instance, days. This is quite usual in technical reports. It is expressed in days from 1 to 365. Why is that? Because the flow duration curve may refer to a period expressed in percentage term, may refer to a period expressed in fraction of the year. So the duration from 1 to 365 is a duration that is expressed as a fraction of the year. Why a fraction of the year? Because usually, and this is something I really want to emphasize, the flow duration curve should give a sketch of the duration of the flow with respect to an average year. Okay? When I say that it can be expressed the duration of a fraction of the observation period, anyway, you should keep in mind that this flow duration curve should give a sketch of an average availability. So if the flow duration period is 10 years, you get basically an expression in percentage terms of what is the flow duration that you may expect on average for whatever observation period. Okay, so if I say 10% of the time I have a given flow that is equaled or exceeded, keep in mind that in order to give a reliable representation, this should be intended as an average. I consider a given observation period, which may be 1 year, and I say 10% of that observation period, on average, I have this flow availability, okay? Of course, if the duration of the actual observation period that I use to estimate the flow duration curve is much extended, now the format, the expression in terms of average is more reliable because, I mean, the observation period is very extended. Let's suppose that my observation period is 10 days. I can still express the duration as a percentage, but of course, it's not an indication of a good average because I only observed 10 days. So when you see whatever duration, whatever the format of the duration is in the graph, maybe a percentage, maybe days, you still have to wonder what is the length of the original observation period that we used to estimate the curve, because in this way you can understand if the expression in terms of average is reliable, okay? So very often, as I said, it is expressed in percentage term, or it may be expressed in terms of duration from 1 to 365. It doesn't matter because, I mean, even the duration between 1 and 365 is, you can interpret it as an average. 365 is 100% of the observation period of 1 year, and 1 is just 1 over 365%, okay? So I just want to emphasize this because you have to keep in mind that in order to get a reliable representation, the length of your original observation period should be very long, and in this way you can interpret the flow duration curve as an indicator of an average water resources availability. Okay, now let's just write D here, and let's don't specify if the duration is expressed in percentage or in days, whatever. And let me draw a flow duration curve. And for instance, it may be a shape like this. Okay, and here. Okay, very good. Now, this is a possible shape, but there might be another different shape, which could be this one. Or we could get a shape like this. Very good. The concept that I would like to emphasize now is quite easy to be understood, but it is important. By looking at the shape of the flow duration curve, you get an idea of the river flow regime. We already said that by looking at the area beneath the flow duration curve, you get an estimate of the water volume during the observation period. Fine. But if you look at the shape, so if you look at more than just the area below the flow duration curve, if you look at the shape, you get some very interesting indications. For instance, if you see that the white curve, it has a quite significant slope in the first part. It means that it rapidly converges to the minimum flow. What does this mean? It means that you have quite a relevant variability in the regime of the high flow. Why variability? Because you see that even for small decreases of duration, let's consider here, for instance, if you decrease from duration D star to duration D double star, if you just with a minimum decrease, you have an important increase of flow, of corresponding flow. This means that you have a high variability of flow, you have a huge change of flow, even for small changes of duration. It means that in the domain of the high flows, you have spikes. You have sudden increases. You change the duration 1 day, and you get an increase of 1,000 cubic meters per second. What does this mean? It means that during that 1 day, you don't know when, but during that 1 day, you had a spike, which was exceeded 10 days, but not 11 days. It means that in 1 day, you had a spike. In 10 days, you had spikes, let's say. This is it's more correct. So you have a high variability. Personally, I'm concerned by a flow duration curve like this. If my home was just close to the river, I look at the flow duration curve like the white one, and I would say, oh, I have to be careful because there are a few days in the years where I get spikes. It's not regular in the domain of the high flows. Let's look at the blue one, the blue continuous line. This is not true in the domain of high flows. I see that it's smoothly changing. The flow is smoothly changing with duration. So if I have the home there, I am more relaxed because I think that I don't have to fear spikes. I don't have to be concerned by spikes. There might be an high flow, but this high flow is quite constant, so I can, in a way, get prepared. And of course, I may have a sharp decrease in the domain of the low flows. This is quite unlikely. I would expect that such flow duration curve closes here. Okay, not really with a steep convergence to the low flows, but it may happen. So for instance, if you have water withdrawals upstream, so maybe that when you have water withdrawal, when people see that they need water, typically they need water when the river flow is very low, and they may start taking more water from the river, so it may be an anthropogenic influence, or maybe the result of particular hydrologic situation. This is less likely anyway. What about the blue dashed line? This is the expression of an intermittent regime, because you have the flow duration curve that is intersecting the horizontal axis. It means that from the duration, let me say here, D 3 stars, from the duration D 3 stars on, if you have 0 here, it means that from this duration D 3 stars on, you have no water. It's dry, which is fine. I mean, it's what we call in Italian torrential regime. It's in Italian, usually we call torrents, which is an international term, but not much used in the international literature. We call torrents the rivers which typically have an intermittent regime, are dry during a certain period of the year, and typically these torrents have a huge variability in the domain of high flows. Sometimes you go to a river and you see that the riverbed is very large, but the river is dry. This is a torrent. It is a bit concerning because if you see that the river is very large, the riverbed is very large, it means that once in a while you get floods, okay, floods that occupy all the riverbed. So if you look at the flow duration curve, I mean, it's a very important information. And this is also why the graphical methods are useful. Still in the era of digital computing, in the era of numerical integration, numerical calculus, some graphical methods are very useful because they allow you to communicate efficiently and also allow you to get an overall view. This is why when we, on Thursday, we discussed about R, I suggested to you that when you get data, the first thing that you should do is a plot. Because the graphical representation tells you a lot of information. It's an excellent synthesis of information. There is a figure in in my web pages. I think it is also in the PowerPoint. Let me share the screen now. I think it's also here, but let me check if it is indeed here. Otherwise, we get it from the web pages. This one. There is a figure that is giving to you an idea of the different flow regimes that you can get from a flow duration curve. You see that there is the low flows, the domain of the low flows, the domain of what they are called intermediate flows, the domain of the high flows, and the domain of the flood flows. I think this is a nice sketch that allows you to get an idea. Keep in mind one thing still. You have to be very careful to get indication on flood flows from the flow duration curve. We are discussing the flow duration curve because here we are interested in water resources management. For this purpose, the flow duration curve is excellent. Excellent. In order to define the high flow and flood flow regime, the flow duration curve, it's not the proper tool. It can give you an idea, but keep in mind that one important thing, which it must be very clear to you, which is the amount of information that you need to define a result. So, what is the amount of information that you need in order to quantify low flows? What is the amount of information that you need to quantify? You need to quantify flood flows. Amount of information means length of the observation period. It means volume of the data that you have available. In hydrology, water resources management, in general, you don't have huge amounts of data of observations for the reasons that I mentioned to you at the beginning of our discussion. I said we didn't start we didn't start far in the past to collect data. We started only recently. Okay, so usually we don't have a huge amount of information. So the question, how much information, what is the volume of the information that I need in order to derive a technical indication? This is a relevant question for engineers involved in water resources management. And what is the rule of thumb? What is the Holy Grail that you have to keep in mind? When you are trying to quantify phenomena in general that occur frequently, you need less information with respect to quantify phenomena that occur very infrequently. This is something naive, you may say. It's naive. It's clear that, if I want to get information of something that happens every day, then it's not a problem. After 10 days, after 200 days, it's perfect. It's something happening every day. Like, for instance, if you want to make a statistics about the timing of the buses in Bologna, you go at the bus stop for 10 days, and then you have a very good amount of information because you get the delay. Every day you get something like 100 observations on delay. After 10 days, you are fine. Maybe that the delays are different on Sunday with respect to Monday, but once that you have been there for a couple of weeks, perfect, okay? If instead you have to get information on earthquakes, what is the magnitude of a possible earthquake in Bologna? This happens like 1 every 10 years on average. And especially huge earthquakes, 1 every 100 years. So you can't just take observation 10 days, okay? This is naive, but it is a very important concept that you have to take into account. So what is the moral of the story if I go there? Flood flows means something that happens like once every 100 years, okay, on average. So if you don't have 100 years of observations, you can't quantify them. If you go in the range of the intermediate flows, this happens every year, a lot of days, So if you get 10 years of observation, that's fine. So the flow duration curve, usually, it's estimated on the basis of a reduced observation period, reduced amount of information. So you have to be very careful in saying, I estimate flood flows with the flow duration curve. For instance, we already uploaded into R the flow duration curve of the Po River. And we computed it on the basis of daily observations for about 100 years, 90 years precisely. Okay, 90 years to estimate a flow duration curve, to define intermediate flows, to define even low flows, ordinary low flows, it's excellent. It's very unlikely that you will have the same amount of data for a river that you are asked by your clients to assess. It's very unlikely. So it's excellent. But still, I cannot say that the amount of data that I gave to you allows you to estimate reliably the 100-year flow, peak flood, okay? Because, as I said, floods occur every 50, 100 years. And therefore, if you have just 100 years of observations, it's not enough. And then you may ask me, and then how do I estimate flood flows? You have a different course to discuss on these things. I just wanted to tell you that with the flow duration curve, with what we are discussing here, we are not concerned about flood flows. High flows may be, okay? It depends on how you define them. For instance, if I want to define the highest flow that occurs on average every year, that's fine. The flow duration curve is perfect. Okay, 100 years of observation, you get the top, the max flow, and you then get the average, that's fine. But it's not a flat flow. The peak flow that occurs on average every year, it's absolutely not a flat flow. We would be really desperate if every year we got flooded, of course. Yeah, question here, and then I translate for the students remotely. Yeah. I repeat.
If I understand well, the slope of our flood is very important because of the flood. This is my question. I don't know which one is more dangerous for estimating that we have a flood in the future. The flood flow area, which is the highest of our flood, or increasing our flood immediately. Which one is more dangerous?
Okay, let me repeat the premise. We are talking here of flood flows that occur on average every year, okay? So not extreme floods, not what we usually call floods. We are talking about high flows. Still, they are important because sometimes there are homes located very close to the river which are flooded like once every 2 years, okay? And in this case, I said that if the first part of the flow duration curve is steep, this means that it's very rapid the development of the flood. Because it means that, for instance, if you think that you have a very steep slope in the first 10 days, if I express the duration in days, it means that I am flooded only 10 days of the year, but this flood is coming up quite rapidly. And this may be concerning because usually, for instance, in the floodplains of the Po River, there are people living there. They are flooded about once every 2 years, but they know that they are alerted well in advance, like 1 week in advance, because the floods of the Po River, they are very slow. They go up very slowly, very slowly. So you don't have a steep flow duration curve. And let me give you an example of the flow duration curve of the Po River on the screen. Let me see where I put it. I think it's not here, so here it is. This is an example. This is not the Po River. This is a river in the northwest of Italy. This is very steep in the first part. It means that here, as I said, river flows are increasing rapidly. Okay, let's look now at the Po River. And this is not very clear, I'm sorry, but these are the flow duration curves. I will take this figure later to give an example, but look at the blue line. The blue line is the flow duration curve average of the Po River. You see that it's not very steep in the first part. Another question
on blackboard, the blue graph and white graph, if we put percent in the x-axis,
yes,
both of them are the same, yes? Because
Yes.
if we put the percent, it can reverse. We can reverse the blue line to only white line, yes?
Yeah, and the question is, if we look at the blackboard that you students remotely connected saw before, there is the blue continuous line and the black and the white continuous line. And the question is, are the percentages, are the durations the same? And yes, my answer is yes. We have the same scale on the horizontal axis. And moreover, we have the same peak flow and the same low flow for the two cards. I wanted to make them equivalent in order to make a comparison of just the progress from the top, from the same top to the same minimum. So different progresses with the same top and the same minimum. But as I said, it is unlikely that this happens, that you have usually when you have rivers that decrease, I think this is an interesting consideration, by the way. If you have a river with a flow duration curve that is slowly decreasing, this is usually a river that has an important water volume. It's a huge river. And therefore, the peak flow and the lowest flow cannot be usually the same amounts with respect to a river that has a flow duration curve that is rapidly decreasing. So let me explain why. If you have a slope of the flow duration curve that decreases slowly, I said you have a huge river. Why? Because typically a huge variability in the high flows is a behavior of small creeks, of small watersheds. Huge rivers usually have a much lower variability. You may ask why. You can get it by intuition, by the way, but the technical explanation is that a huge river makes drains a large watershed. In a large watershed, you have a mix of different conditions, a mix of climates, and therefore it's an average of different situations, which means when you take an average, usually you reduce variability, isn't it? You get a sequence of data and you get the average of it, you put variability to 0, okay? Because from a sequence of data, you get one number. The same for a river. If the river gets water from a large area, then in this area, there are high variabilities. Think of rainfall. Rainfall is not evenly distributed. It's oddly distributed. So in some part of the catchment, you may have a storm. In the other part of the catchment, if it is large, you may have no rain. And therefore, the river makes an average. And this average smooths variability. If you think of a small creek, you may get a violent storm which covers the whole creek. And this provokes a sudden flood because the violent storm is short, 5 minutes. So you don't have any possibility to predict it. You know that the storms, the summer storms, they are very difficult to predict, even for meteorologists. You get a sudden storm, it lasts 5 minutes, because we know that summer storms usually they last 5 minutes, but they release a lot of water in these 5 minutes. And if they cover the whole catchment, you get a flash flood. And this is why, for instance, in Italy recently, we got several flash floods in small catchments because we got several violent storms. Storms of long duration, not changed much, but after climate change, we suspect that violent storms have increased in violence. I hope this answered your question. And what the concept, the overall concept that I want to give you is that your mission is understanding a natural system. And you have to be very good in using at best the information that you have. So the concept that I wanted to to discuss today is, okay, we learned this graphical tool, flow duration curve. Let's now learn how to get immediately a perception of how nature works behind this graph. This is your mission. Okay, you work with reduced information. You have to use all the information available. And you have to know how to extract the best from it. Okay. Now let's look at the technical part. How can we estimate the flow duration curve? And so let me go back to my PowerPoint. Here. How can we estimate it? First of all, let me make it very simple. Okay, we will in R we will do it for the Po River. You will see that it's a trivial task. Okay, but after having learned how to perform this trivial task, we have also to make some additional reasoning in order to better emphasize the concept. Again, the reason why I stick on the concepts is that if you know the concepts, you know how to extract the best of the information. It's not just that I want to make the theory because I am a fan of the theory. For instance, here you see a mention to probability, and you may say, this is very boring. Indeed, it is very boring. But the reason why I am mentioning probability is that this is an excellent way in this context to extract information. And again, I'm not mentioning probability because I am a fan of probability. I'm mentioning probability because I think that it helps you to get the concept. And this is really what I would like to teach you, how to get the concept behind this fascinating phenomenon. We are talking about rivers. It's some of them. Maybe it's one of the most fascinating elements of the natural environment, water, rivers, etc. I just want that you get the concept behind it. Okay, now let me just start by explaining how the flow duration curve can be estimated. And this is a first possibility. We will discuss two methods. As you will see, it's very trivial, okay? Now, let me work on the blackboard again. You don't need the screen shared now. You can pin my video if you want to see the blackboard better. And students remotely connected, just let me know if you have problem by looking at the blackboard, etc. I don't think, I will not write much, so it shouldn't be a problem, but just let me know if, okay, first of all, we need data. Okay, let's suppose that we have data, because there is another interesting question. If I don't have data, what should I do? Let's postpone this, okay? Now, let's suppose that we have data. Let's suppose, what are the data? River flow. River flow, let's suppose that they are collected at daily time scale, and let's suppose that we have 10 years, okay? So let's forget the 29th of February. If we have 10 years of daily data, we get 3,650 observations. Let me just write here, no 29th Feb. Okay. Now let's put them, for instance, in Excel from 1 to 3,650. I put my Q. Okay. So here I have Q1. Here I have Q3650, and in between I have all of my numbers. Very good. Now, let me Now here write another column of the ranked queue from max to min. Okay? Or let me just, I write again, let me delete the last one. I want to make it more clear. Q max, Q min. This is trivial. Okay, perfect. This is my vertical axis of the flow duration curve. Okay? Now I need the horizontal axis. So this is my D. And let me now, let's suppose that this is time, or let's call it, yes, time. Let's put a T, capital T there. What is D? D is T divided 3,650 times 100. This is D percentage. The last one is 3,650 divided by the same number is 1 times 100 is precisely 100. So you see this is varying from something that is less than 1% and goes up to 100%. Perfect. Now I just need a graph of ranked Q, with respect to the percentage. That's it. The most complicated thing is to rank the observations in descending order. It's very trivial, very trivial. Okay, and this goes to, we can put here 0 and here 100%. Zero percent, 100%. If 100% is here, and the first number is not 0, it's close to 0 because it's 1 divided by 3,650 times 100, so it's something like 0.0 something, so it will start from here. And the flow duration curve will be something like, I don't know, it starts not from the axis, it started from the first point and it goes down to the last one. Very easy. In Excel or in R, it's very easy. It's something that you do in like 5 minutes, no more, including the graph. Very good. And if I go to my next slide and I share the screen, just 1 second, I share it. This is my next slide, and if you see what is explained here, it's precisely what I did on the blackboard. Pool all observed stream flows in one sample. Rank the observed stream flow in ascending, here it's in ascending, but it should be in descending order. Sorry for that, because this is, you can also use the ascending order, but then you have to invert. I think it is clearer as I explained in the blackboard, in descending order. You have to rank the observed stream flows, identify the position of the observation in the ordered sample, which coincides with an estimate of the duration. Let's forget, here it mentioned probabilities, let's forget it for now, and plot each ordered observations versus its position. It's precisely what I did, okay? Now, let me just go back one slide and talk about probabilities. I don't want to discuss probabilities now, but let me just I say one thing. I think some of you already know what is probability. Some others probably not. You have different backgrounds, so it's not a problem. It's not a problem whatever, if you know it, you don't know it. What I will do in the next lectures is to recall some basic concepts of probability, only those who will serve to us in order to discuss the next lectures. However, keep in mind that probability is an essential tool in water resources management because it's a very good way of extracting information from data. There are other methods for extracting information from data. Probability is the most classical one. You may have also heard about fuzzy logic or something like neural network, deep learning. This is very fashionable today. Machine learning, deep learning are almost synonyms. They are alternatives, are very good ways of extracting information from data. What is the basic difference? Probability was specifically conceived to extract information from reduced amounts of data. Deep learning, as the term suggests, and also machine learning, they need more data to work. So probability, this is why it's essential in our field. But just let me make clear one thing. Probability has a complicated theory, but the purpose of probability is very simple. So just keep in mind what is the purpose of probability, because it helps you in understanding everything related to probability. Probability is the study of the frequency of something happening. That's it. That's it. Frequency of something happening. What are we talking about now? Flow duration curve. What is the flow duration curve? Is an estimate of the frequency something is happening. Precisely the same thing. So probability, it's the same thing as drawing a flow duration curve. When I draw a flow duration curve, I precisely do something that is probabilistic. Why? Because I'm studying the frequency of something happening. And this is something that is inherent in the human behavior. When we say experience, what is experience? Is knowledge, okay, it's knowledge, but what is experience in essence? Is studying, knowing the frequency of something happening. Sometimes we say, I am experienced in designing, I am experienced in structural mechanics. What does this mean? I am studying the loads on a structure. The loads are precisely something happening with a certain frequency and whatever. So probability is very simple, and so you don't have to be concerned. I don't really want to now to discuss about it. I just want to say that the flow duration curve is nothing else than a probability distribution. And because for the reasons that I just said, it is studying the frequency of something happening. Okay, but for now, stop probability, and let's again, discuss how we estimate the flow duration curve. There is a second method, a second possible method. It is something that you may also devise yourself by intuition. What did I do on the blackboard just 5 minutes ago? I put all the data together and I, in a way, estimated their frequency. Okay. But if you think with a technical perspective, if you approach the problem with a technical perspective, what is our purpose? Our purpose is to estimate what happens in an average year. When we study water resources management, we usually refer to the yearly period. Because if you think what are the problems of water resources management are the dry season. The dry season, we are referring to a specific part of the year. We are not really interested in knowing what happens once in 100 years. We are interested to know what happens in the dry season every year. So what is important for us is to estimate what is the progress of water resources during the year. So if we have 10 years of data, like the example that I did before, you may get this idea, why should I put the 10 years of data all together? Why don't I estimate for every year my flow duration curve and then take the average? Because you are interested in learning what happens on average every year. So another possibility could be precisely what I just said. You have 10 years of data. For each year, I estimate the flow duration curve, and then I make an average. This is precisely the second method. You already know how to estimate the flow duration curve with 10 years of data. You repeat the same experiment in every year. And then you take the average. What do I mean? Let me just go back on the blackboard. Okay. You also, who is in the room, you may also see on the screen the next slide, which is anticipating what I'm doing. But for those who are connected remotely, look at the blackboard, which I'm cleaning now. And so let's draw our 10 flow duration curve. I draw on the blackboard only 3 of them, okay, or 4, let's say. So I have Q, I have D, and then I may have like my 4 flow duration curve. This is 1. Let me get. This may be another one. This may be another one. And this may be another one again. Just 1 second, I just want to try to make something. And this may be another one again. Okay, they are different in shape. They can cross each other. No problem at all. Now, for each duration, and just let me emphasize one thing. These are annual flow duration curves. Annual flow duration curves. Okay. Good. Now let me emphasize one thing. Let's suppose that we express now the duration from 1 to 365 and not in percentage terms. It may be justified because these are annual flow duration curves, so one may avoid the additional computation of expressing the duration in percentage. We have already the duration expressed in days, so let's just write here 365. What would be the start? What would be the abscissa of the first points? It's 1, correct? And what is the resolution of the horizontal axis? It's 1 day. So the second data will be 2 days, and then 3 days, and then up to 365. The resolution is 1 day. Okay, very good. Now let me compute for each duration the average of the curves. And so I get something like, I'm not sure if I am precise, but and I will just make it thicker, okay? This may be the average. Okay, very good. And this is my average flow duration curve. You see, it's very simple. It's a bit more complicated with respect to the other method, because in the other method I have to rank only just one sample. Here I have to rank several samples and then compute a final average. But the result, if you try, once that you will be able to work in R and compute flow duration curves, you may try to do that. The result is similar. Now, what is the reason why then I should use the second method instead of the first one? If this one is a little bit more complicated, why should I use it? Because it gives an information that the previous method doesn't give. What is the information? The information is variability. For each duration, I get the estimated flow on average, but I get also an estimate of the variability, which is important because the average water resources availability is a good information, but it's not enough for us. We also need to know variability. So I have a river flow of 100 liters per second available on average for 100 days during the year. Fine, okay. But what happens every single year? In a single year, I may have not 100 days of availability, which is the average. I may have 70, or I may have 150. Now, if I see that the variability is reduced, I am less concerned because I know that the average is available almost every year. If I see a huge dispersion of the curves around the average, it means that there is variability. So I have to be careful because it means that for most of the years, I could have less than the average, much less than the average. So in this way, I estimate variability. And then you may think, if this graph gives to me additional information, for sure I am losing something. Because the data from which I started are the same data. The amount of information is the same. So if I have two methods, and the second one gives, on the one end, an additional information, it means that on the other end, is missing some information. What is the information that is missing here with respect to the first method that gave to me only one curve? Okay? The information that is missing is the resolution of the duration. Here I have a resolution of 1 day. 1, 2, 3, 4 days. With the other method, I had a resolution of 1/10 of day. Just think at it. Let's not to get into much details about that. Think at it, because it is very easy. And if you make an exercise, you try, you look at the duration, whatever you express it in percentage or in days, you will see that the second method has 1/10 of the resolution. The 1/10, yes. And the first method has 10 times the resolution. Do you have a question in the room? Yes, please.
Professor, when we have a variability, it means that our river unpredictable.
Oh, let me think how to answer this question. The question was, where I have more variability, the river is unpredictable. Let's say more unpredictable. Okay. I wouldn't say that is less predictable. I just would say that the prediction is that you have an average water resources availability with huge or limited variability around it. I mean, I'm thinking how to reply to your question without taking probability calculus into play. It means that, for instance, let's suppose that you don't want to estimate, you don't want to just estimate the average water resources availability. And let me make an example. Let's concentrate on the duration of 30 days. And I tell you, on average, every year, for the duration of 30 days, you have, on average, 50 liters per second. And then you may ask me, okay, but tell me, how many years, in percentage terms, I have less than 30 liters per second? And I tell you, you have less than 30 liters per second on 1% of the years. Or, second answer, you have less than 30 liters per second during 30% of the years. In the second case, you have more variability. And the prediction, I think it is accurate anyway. It's not limited predictability. It's just the fact that you have at the end of the story, a higher risk of not to get the average outcome. To give you another example, I may say, let me think of, I may tell you, for instance, this is a river where people who go to catch fishes, on average, they get 10 truths per hour. But I may also say, be careful, because 40% of them get less than 1 truth per hour. Or I may say, look, on average, they get 10 truths per hour, and 90% of them get at least 8. Of course, you prefer a more stable situation. But I wouldn't say it's limited predictability. Okay, now let me share the screen, because I think that you got an idea of what is the additional information of the second method. Let me share the screen now. This is an example of what I just said. You see, forget about the blue lines for now. And let's look at the red line and the gray thin lines. The gray thin lines are individual flow duration curves, and the red one is the average. So this is an example of application of the second method. Now, you see, now let's discuss about the blue lines. What are the blue lines? The blue lines are, and here I am replying to your question again. The blue lines are those who are exceeded only 5% above and 5% below. What does this mean? It means that for each duration, I not only compute the average, I compute a band that is encompassed by 90% of the observations for each 90% of the curves for each duration. I just discard the upper 5% of the curves and the lower 5%. It means that I don't only compute the average, I also compute a band where 90 times over 100, I have the flow. Now, if these two blue lines are very wide, it means large variability. If they are very compressed on the red line, there is a lower variability. Predictability is the same. But of course, you know, here I have quite a large dispersion, so I am a bit concerned. But still, they are very useful because they allow me to say to my client, look, 90% of the time you have a flow available that is given by the blue band. For each duration, 90% of the years, you have this flow available. This is an essential information for technical design. If you design an hydropower plant, you are not interested in the average power that you get from it. You are also interested in knowing the minimum power that you get 90% of the years. And this is the indication of the lower blue band. You see that there is an indication P equal to 0.05. Actually, it just means that I discarded the 5% lower curves and the 5% upper ones. It is indicated with P and not with F like for frequency, because P is the first letter of probability, because what we are estimating here is a probability distribution. For each duration, we are studying the frequency of something happening. I repeat again, for each duration here, we are studying the frequency of something happening. What is the something? Is river flow available for that duration. And therefore, it's a probability distribution estimated for each duration. Good. So we have learned the two methods to estimate a flow duration curve. This is a classical question at the exam. What is a flow duration curve? How can we estimate it? What is the advantage of the first method? What is the benefit? What is the benefit of the second? What is the limitation of the first? What is the limitation of the second? The limitation of the first method is that I don't have an estimate of variability. The limitation of the second method is that the resolution is lower. Resolution in terms of duration. Good. Questions? Okay, let's move forward. Now, we already discussed a little bit this. So, how can we estimate then? I have a flow duration curve. Okay, good. How can we estimate the design water withdrawal? It depends on the use, of course, and you see the first bullet point, depends on the water use. The water use may be hydropower generation, maybe irrigation, maybe water supply. And so I give you just a rule of thumb here, and I think we discussed a little bit already, but let me just give the rule of thumb. Usually, and the rule of thumb refers to hydropower plants, but it is also useful for, it is also a good indication for water supply. And an order of magnitude of the design flow is the river discharge with a duration of 60 days. And 60 days means that I am expressing the duration in terms of numbers from 1 to 365, 1 year. So 15, 10, 20% of the duration, a duration of 15, 20%. This is the rule of thumb. And keep in mind that if you want to go beyond the rule of thumb, you need a cost-benefit analysis. So depending on the water use, you estimate the construction cost and the management costs of the plant, of your project, and then you estimate the benefit with, they may be economic benefits, and therefore you compare the costs with the benefits. It is not only economic cost-benefit analysis. Sometimes you have to consider issues that are not quantifiable in monetary terms, like environmental impact or like disturbance to the wildlife or disturbance to the citizens. An hydropower plant is noisy, and therefore, and also the construction has an impact on the environment, the construction phase. And I'm just anticipating that when you have to evaluate non-monetary benefit and costs, you of course cannot refer to the monetary values, and you have to use different methods for evaluating costs and benefits. We will discuss at the end of the course what are these different methods. They make use of utility functions usually, which I think you already discussed in other subjects maybe. But let's not anticipate this topic because it will be a subject of discussion later on in April. Once that you estimate the design flow, you can estimate the water volume that you get from a given river in view of the related flow duration curve. Let me look at the next slide. This slide is a little bit, we need to dedicate some time because it's a little bit not complicated, but requires some thinking. And before I discuss this specific figure, let me refer to the blackboard again and emphasize, show you once again, because we did already last time, what is the water volume that I'm getting from a given flow duration curve and a given design flow. So let me go to the blackboard again. And let me clean it. So let's suppose that we have this flow duration curve Q, D. D, let's suppose that it goes from 1 to 365. So we have this flow duration curve, which is like this, for instance. Good. And now let's take the flow with duration of 60 days, 60, as design flow. Let's put it here. QP, okay? Now, let's suppose that we have this situation. What is the volume of water that we can take with this project? The volume, it is given by the area, sorry. Okay, the area beneath the flow duration curve and beneath the value of the design flow. So it is given by this area. And I think we all agree on that. Let me just finish to put the area in evidence. So one may say, okay, the problem is very simple. Of course, I cannot get the part of the area below the flow duration curve that refers to the flows that are higher than my design flow. These flows are released into the river because I can't get them. If my design flow is 100 liters per second and the river delivers 200 liters per second, I only get 100. And the other 100 are released along the river. And in a way, from the point of view of taking water, this area here is lost. This one is lost, okay? Actually, it's not lost, it's released into the river, but anyway. So you may say it is very simple. I just estimate this blue area, and that's it. But there is environmental flow. There are the environmental flow requirements. And what are the environmental flow requirements? The environmental flow is the flow that you have to release into the river in order to preserve the aquatic environment. And there is a precise definition on my web pages. Please learn it, because this is another question for the exam. What is the environmental flow? It is a simple one, but actually, given that it's a definition, sometimes the students have some problems in remembering it. Now, what does this mean? It means that you cannot take the whole water from the river. This concept of environmental flow was introduced only recently. The first was the European Water Charter that we mentioned, that in a way mentioned that water is essential, blah, blah, blah. And it was precisely during these years that people became concerned by the impact of water withdrawal, because before then, 1968, before the 60s, usually the purpose of the projects was to get the total amount of water. Of course, because water is necessary, and therefore, whatever is the use, it was not just a matter of seeking an economic interest. It was a matter of seeking the max benefit, social benefit from water, and therefore they basically tended to get all of it. But then they realized that the impact was enormous. At the beginning, it was not so relevant because there were only a few dams. But afterwards, the number of dams increased a lot, especially in mountain areas. And therefore, there were concerns. And the first Italian legislation, which pointed out indirectly the need of releasing environmental flow, was the Legge Merli, it's called in Italian, but you don't have to remember the name. It was issued in 1976. And it was issued not by making direct and explicit reference to the aquatic wildlife. It was issued in order to limit the water pollution. Because what was the problem? The problem was that the sewer systems were releasing the effluents into the rivers, and then the rivers were deprivated by water. And therefore, the concentration of effluents increased and became unsustainable. So the Legge Merli said, you have to keep the concentration of effluents limited. First, you have to monitor them. Before 1976 in Italy, but also I would say in most European countries, there was no legislation imposing to the authorities to monitor the quality of rivers. There was no legislation. Then they realized that the rivers got really dirty, polluted, and therefore the legislation said, first, any responsible authority for a river body, for a water body, has to monitor them. I say water body because it applied not only to rivers, but also to groundwater. And therefore, the Legge Merli said, you have to limit the concentration of some effluents. And what is the way of limiting the concentration? Releasing water, releasing more water. And then there was the first law who prescribed the release of the environmental flow in an explicit form was a decree I don't know how to say in English, but it was a decree, it was a law, you can call it a legislation, issued in 99. It's the number 152 of 99, but you don't need to remember this, which was an anticipation of a European directive, which is the Water Framework Directive. We are not really, I'm not interested in that you remember legislation, but I mentioned the Water Framework Directive because it's a very important European deliberation that regulates and fixes obligations on water resources protection over the whole Europe. Let me just see, because I got a message in the chat. I don't have anything to share actually. I'm just because I'm working on the Blackboard. So the question was on the chat, can you share your screen? I think you need to look at the Blackboard. In the screen, there is nothing relevant. And I'm just now making a discussion which is not a subject for your exam. I just want that you know this Water Framework Directive because it is very frequently mentioned in water resources management. But it's not described in my web pages because I don't want to discuss legislation here. It's only technical issues. Okay, so the environmental flow must be released, which means that you cannot dry the river. So what does this mean? It means that I cannot always take my design river flow. First, because I can get it only for a duration of 60 days, in any case. And then in the river, I have less water than the design flow. So for the remaining days from 60 to 365, in any case, I cannot get the whole of QP that you see on the Blackboard. And I have to take into account that I cannot dry the river. So there is a base in this graph that you see on the Blackboard that I cannot take. Let's highlight it. So let's first of all put the environmental flow here. Q, and let me call it DMV, okay? DMV, because in Italian it is frequently indicated with the acronym DMV, or you may use another acronym, but let's indicate it here. And let's put an horizontal line in correspondence of it. Okay, so this allows me, this horizontal line, to highlight an area beneath below the environmental flow that indicates a water volume that I cannot take. And let me identify it with the white lines. This is a volume of water that I cannot take. Why I am stopping here with this highlighted area? Because in this part of our flow duration curve, for durations that are lower than 60 days, for durations that are lower than the duration of my design flow, I have some excess water into the river, which helps me to release the environmental flow. Okay? I mean, I don't need to release the environmental flow for a duration of 1 day because the environmental flow is already given by the excess water flow into the river with respect to what I take. And therefore, if I also took off this whole area here, it would be too much. Some part of that volume, I can take it. I can release my environmental flow. I can, decrease my environmental flow because part of it is covered by the natural river flow. Okay? And so, how can make a precise estimation of the volume that I'm losing to release the environmental flow? If I take the whole of this area, I am too conservative. But if I only take this one off, I am depriving some of the environmental flow. So I have to make a mix between this big rectangle here and the bigger one here. I have to make a mix. How to make this mix, for instance? For the duration of 59 days, let's suppose that the duration of 59 days is here, 59. What is the environmental flow that I have to release? Okay, let's see. I should give an environmental flow which is equal to Q dmV. But if I go up, I see that I already have some environmental flow that is released by the river here. So I don't need to release the whole of the environmental flow. I have to release the whole minus this part here. So I bring this part here down here, and this is what I have to release. This is what I have to release, which is total of the environmental flow minus this segment here. And I have to do that for any duration. So at the end of the story, what I have to do is to estimate something that looks like this. And then this is the volume that I am losing for releasing the environmental flow. Now, before making the break, let me do one thing, because I think that this issue, this point, could be not really well understood. So I'm making a zoom. Okay, so the zoom, let's make it here. And what I want to do is to get this part here and zoom here. So, and then I'm checking if it is in the video, just 1 second. Yes, it's there. Okay, this is 60. This is my DMV, QDMV. This is my QP. Good. And now let's suppose that we have to solve our problem. So how to estimate this small triangle, let me call it in this way, that I estimated in my first figure. I think that, let me just think. Okay, let's do that. Okay, now, so the question is, what is the amount of this area that I have to release for granting the environmental flow? Not all of it. Okay, the method is this one. You take QDMV, the value of QDMV, and you bring it up over QP. So this segment here, it's again Q D M D. You bring an horizontal line here until you intersect your flow duration curve, and you identify in this way a volume here, which is a quasi-triangle, okay? It's not a triangle because the flow duration curve is not a rectilinear segment, but it's a quasi-triangle. Perfect. Now, this triangle has to be mirrored down here. And then, this is the estimate of the area that you have to release to grant the flow duration curve. This means repeating for every duration the same reasoning that I did for the duration of 59. Okay, so basically for every duration you estimate the length of the segment between the QP and the flow duration curve, and you subtract it down here from the QDMV. Now we make the break, you think at it, and then when I come back, you tell me if you have any question. Look, before I go for coffee, this is very simple, but understanding requires some reasoning. It is just a reasoning of plus and minus. You don't need integrals or whatever. You just need to think that every day you have to release, every day of the year, you have to make sure that in the river you have the environmental flow. And this environmental flow is either released by the river naturally, because the water flow is exceeding what you are taking, your design water flow. And if it's not released naturally, you have to release it by reducing what you take. And this is just what we are doing here, okay? And please get this concept, because this is something that it's at the exam may be asked. And it is not really relevant in quantitative terms. We are talking about very small volumes of water, but it's the concept that is relevant, and also the concept of environmental flow. The fact that we really have to be committed to make sure that we release the environmental flow. On the other hand, we are engineers. We cannot lose water resources. If we make a project, a plan for using water resources, we have to use them. So it's not a good approach to say, let me take just a minimum amount of water because I want to protect the river. No, we have to protect the river, but we have also to take the most of water resources. And this is the concept that brings me to explain what is the technical computation that you have to make in order to make sure that you have the environmental flow, but you are using the most of the water that you are interested to use. Okay, 15 minutes. And then I get questions. Okay, questions? Let me just check the chat. What I just depicted drawn on the blackboard is also reported in this slide, which provides a copy of a figure that you can find on the web pages, and you see that there are two yellow volumes with written these two volumes are equivalent, and the brown area is what we can withdraw, the volume that we can take with the project. And the areas below the flow duration curve that are left in white are the areas that we cannot take. The upper one, because there is more water than the design flow. And the lower one, because it's the amount that we have to release for the flow duration curve. Okay, and there is a question in the room, yes?
Why not simplify the graph and make him QP plus the base flow, so you don't have to drop, because like now it seems like you can take more than what is, I don't know, it seems absurd to put the area down when you could just elevate the level.
Okay, I'm just, so you are suggesting to simplify it by taking the environmental flow and above QP, correct?
No, I'm intending to put QP higher so that it doesn't take into account the environmental risk.
Because I think it wouldn't give, the question is, why don't you simplify the graph by increasing QP of a quantity that is compensating the environmental flow that I have to release? Because I think that, the design flow is something that has a precise definition, which is the flow for which you designed your hydropower plants, the machines, the pipes. So I think that if I increase the QP, this means that I would have to design a pipe for bringing water downstream, which it's not really needed, because what I can bring downstream is something less than that, because I have to keep something into the river. So I don't think it is, I think we have to highlight what is the design flow, and we have to also highlight when I need to release an environmental flow, because the environmental flow may be released through gates, something that is maneuvered, and I think it is important to highlight what is the duration of the time when I have to keep the gates open. And also, if one wanted to simplify this graph, one may just say that for providing an estimate of the water volume that you are taking, the environmental flow is representing something like 3%, maybe. So we could also say that the whole area, without taking off the environmental flow, without removing the white area in the lower part, is already a good indication, because keep in mind that when you talk about water resources management, uncertainty is always something around 10–20%. And therefore, if you make an overestimation of the volume of water that you can take of 2%, it's not really something important. So if I wanted to simplify it, I could tell you, just forget about the environmental flow. Take the area below the design flow and below the flow duration curve, and that is a very good estimate of the volume of water that you can take. On the other hand, I think it's important that we focus on the concept. And the concept, I mean, how the whole intervention is to be managed. So you have to consider a design flow which allows you to size the infrastructures, pipes, plants, etc. You have to consider a design, an environmental flow, which is extremely important that you keep into the river for the aquatic wildlife. But you have to be concerned about the environmental flow only when you don't have enough water into the river. When for those days where you have enough water into the river, you don't need to be concerned by it. So I think the whole of this reasoning is a bit complicated, but it gives to you an idea of how the system works. This is what I'm really interested that you understand. And I think it is important that you understand the combined working of a natural system, which is the river, and an anthropogenic system, which is your project. You have to understand the combination between the two, because if you understand the combination between the two, you get also an idea of sustainability. And I like this graph because it focuses on these two systems as they were a unique system interacting each other. Other questions? Yeah.
Sorry. In reality, we just know the part of the environment, the volume of the water that we need to give to the environment, and we know our demand, and then we just simply minus our demand from the whole volume and get the environment. In the reality, we do this. It's just perspective. We want to know what's going on. Yes.
Yes. In reality, the question was basically, in reality, what happens is that we have water demands from population or whatever, irrigation. And then we have water demands, fictitious water demands from the river. And we have to combine them. And the question was more a comment than a question was, this graph gives an idea of how they combine together and gives an idea of both the demands that we have to satisfy. Yes, I think this is precisely what I meant to, the concept that I meant to deliver. So understanding how they work each other. And also, you have to take into account that, first, the water demand is estimated on the basis of demographic analysis, projection of increase of population, projection of increase of irrigated area. Fine. Environmental flow is usually estimated by law. You have a legislation suggesting what is the amount of the environmental flow. And this is what you have to do. You are not required to estimate the environmental flow. You are required usually to estimate the water demands. The environmental flow is given by legislations. And these two things are often seen as not related. The modern approach to water resources and the modern approach to sustainability is to try to understand that actually they are related, because if you reduce the environmental flow, you may increase the water demands. Why? For instance, because if you release less water into the river, you may get a depletion of groundwater resources, which are less recharged. And therefore, you have an increase of the water demand from surface water resources. So they are not completely independent. Conversely, if you reduce the water demand from population, you may also get a feedback on the environment. because environment and population are strictly related to each other. And therefore, if you have a greater increase of population, you may have the need for an increased environmental flow. Because, why? For instance, for diluting the pollutants. So these two things are actually intimately related. And you can understand how they work together only if you consider the natural system and the anthropogenic system as a unique entity. This is the modern approach, which is a reasoning that I would define philosophical. But it is important to understand that we are not talking of two separate things. If we want to focus on sustainability, we have to focus on a unique system without identifying a good and a bad, because typically what we consider, which is, I mean, I understand why, is that the anthropogenic effect is the bad and the natural system is the good. Actually, they are not competing, they are evolving together. And this is the modern philosophic approach to sustainability. You have to try to focus on this system as a unified entity. Okay, but now let me go back to the technical. Do you have a question in the room? Yes.
Professor, I didn't get the small portion of the plot that we added for environment, and I didn't get it why we added that one.
Sorry, why we added what?
The small portion we added the secure
the yellow one, you mean?
Yeah.
Okay, the upper yellow is not added. It's just mirrored down. And what is instead the yellow, the lower yellow, this is added to the volume that we get. I realize and I acknowledge that this is not very clear from this picture. I think this picture, which I just wanted to, I already wanted to modify last year and I forgot, has two limitations. First, it doesn't make a difference between the two yellow areas, and the upper one is not added to the curve, while to the brown area, while the lower one is added. And I think I need to make a difference in that. And the second thing, I think it should highlight the value of the environmental flow above the QP that allows me to identify the upper yellow area. And I think I have to modify this.
And why we add this?
Why we add what?
Why we add this to the environmental, we consider the environmental flow in the after 60 days in the low developed plot. So we added to the flow we want to do this.
Yes, because it allows you to estimate the yellow area. So let me see if this doesn't take much time to me. Let me open a OneNote, and let's see if I can modify this. One second. Here it is, sorry. Okay, let me see. Okay, this is perfect. 1 second. Oh, this is slightly different. Yeah, this is actually, I forgot this. Last year I corrected. In the website, it's correct. Let me just, in the website, it was corrected. It is in PowerPoint, which I mean, sorry. Okay, give me 1 second because I'm copying the figure from the website. If it is not too slow, just, okay, this is perfect. 1 second again. So in the website, you see that correctly I identified the two triangles, and only the lower one is depicted in brown. What is still missing here? It's let me just 1 second. Doesn't work. 1 second. Drawing. Okay. Blue. I think I should put here the DMV. So the DMV, it's about here. I should put here the DMV. Let me see if DMV. Okay. And I should put a horizontal line here. One second. I don't think with the finger. Okay, with the finger it works better. I'm sorry, but I'm not used to work with. Okay. Okay, this is perfect. I should put here the DMV, and let me just write here DMV. Okay, I should put the DMV here, which allows me to identify the red triangle, which is to be mirrored down. I hope I answered your question. Okay. Just 1 second, I'm checking if there are questions in the chat. No, perfect. Other questions? Okay, good. Now, 2 things. Further consideration. Once you computed, and let me go back, the volume of water that you can take, the volume of water, okay, the brown area, it's possible to estimate the average flow that is withdrawn, which is given by the brown area, which gives the volume, divided by the duration of 365 days. So if you get the estimate of the water volume that you get during 1 year, and you divide it by the duration of 1 year, you get the average withdrawn volume, which is lower than QP. It's lower than the design flow. It's lower because the design flow is only taken for 60 days. Okay, so you can estimate what we can call QMP. I can write on the blackboard just QMP, which is given again by the brown area divided by the duration of 1 year. Remember that the flow is volume of water per unit time. So basically QMP, I'm writing on the blackboard, but I'm just writing QMP, which means M stays per average, mean. This is given by, again, the yearly volume divided by the duration of 1 year. And this is also useful to say to your clients because they want to know an estimate of the design flow, which is the max that they can take from the river. They need to know the duration along which they can take this maximum, and they need an estimate of the volume that they can take for 1 year, which is equivalent to the average water, the average flow, the average withdrawal flow. Okay, it's just the volume divided by the duration of 1 year. Now, once that you have all this information, you can compute 2 indexes. And the 2 indexes are the water withdrawal index, and the screen is shared. So what you see remotely is the same thing that they see in the room. The water withdrawal index is given by the design flow QP divided by the average river flow QM. Okay, average river flow QM. Average river flow is simply the average of your river flow data. It's the natural average river flow. Perfect. And then there is a second index that you can compute, which is the water use index. Is given by the ratio between the average withdrawal flow divided by the average flow. Good. If I asked you, what is, in your opinion, the range of variability of these two indexes? Let's start from the second. If you have a design flow of 0, you don't take any water, both indexes are 0. Okay, so the lower value for these two indexes is 0. What about the upper value? Let's start from the water use index, the second index. The upper value is 1. You cannot take an average flow that is greater than the average river flow. Or, let me say in terms of volume, you cannot take a volume of water that exceeds the volume of water that flows into the river. And therefore, the upper value is 1 for the water use index. So the range of variability for the water use index is 0, 1. What about the water withdrawal index? Actually, there is no upper limit to the design flow. You could take a design flow which is infinite or infinite. I don't remember. Every year I have this doubt. Every year I listen to Google, so next time I will take the correct pronunciation. And it can be infinite, and therefore there is no upper value to the water withdrawal index. So the range is 0 plus infinity. Actually, if you look at, I go back to the graph of the flow duration curve. You can guess where is the level of the average flow of the river, because the average flow of the river is something that is for sure lower than QP. You can think of the average flow of the river like the flow with a duration of 180 days, half of the duration of 1 year. And therefore, you see that it depends on the slope of the flow duration curve, but the upper value for the water withdrawal index may be 2, 3. You don't go to infinity because it is not really convenient, okay? But remember these two indexes. This is another question that is maybe asked at the exam. They are useful. They are useful because they give you an idea of what is your usage of water with respect to the river capability to deliver water. Good. My website, my lecture in my website closes with some examples, of a water withdrawal which is the hydropower plant of Isola Serafini on the Po River. Let me just see if I have a picture, an aerial picture of it. I go back to Isola Serafini. Now, how does it work, this hydropower plant? So look at the bottom left, the red rectangle, and you see that there is a meander of the Po River. So upstream is, where is my mouse now? This is upstream. The natural course of the Po River follows the meander. Look at my mouse. And there is, during this meander, an elevation gain. So during the meander, the river loses some elevation, gain in a negative, with a negative meaning. So the idea was to cut the meander and to keep some environmental flow during along the meander. But if you look at the colors, this is I think it's not an aerial picture, but the colors reflect the amount of flow. Most of the flow is diverted along the cut. Along the meander, they keep just an environmental flow. And what is the effect of the cut? The effect of the cut is that you create an hydraulic jump, because given that the cut is barraged, they put two barrages, one on the cut and another one at the beginning of the meander. Here you see look at my mouse, this is the barrage at the beginning of the meander, and this is the barrage along the cut. So the barrage along the meander serves in order to regulate the flow in the meander, so to reduce it. And then you have the barrage on the cut, which creates an hydraulic jump, because you have a difference in elevation between upstream the meander and downstream the meander. And in the barrage on the cut, they put the turbines in order to generate the hydropower. This is the only barrage located along the course of the Po River. The downstream course of the Po River is not barraged. Contrary to the other big rivers of Europe, they are all barraged. The Po River has only one barrage. They have dams upstream, but much upstream in the tributaries, but along the course of the Po River, from Turin to the delta, there is only this barrage. This is a distinguishing feature of the Po River. So you see here the big picture. There is the dam and the diversion canal with the two barrages. Okay, and here in the barrage on the diversion canal on the cut, there are the turbines. Perfect. This for this project, let me go back to slide. You can basically depict in a graph that is similar to the flow duration curve, in the same graph, several additional information. This is not something that I asked at the exam. I just want to give you an example of a graphical representation that gives really a lot of information. First of all, there is the black thin line, river stream flow, FDC, flow duration curve. This is the natural river stream flow, okay? And then there is the design flow, the thick black line, 1,000 cubic meters per second. And you see that with the black thick line, they depict here the usable discharge. Usable discharge, okay. And the environmental flow here is not depicted. It's released along the meander. And in any case, this is a run-of-the-river plant, which means that they continuously produce hydropower. And therefore, they are not deprivating the river of flow. There is no need to consider here the environmental flow, because they are continuously turbining. So there is a continuous release, okay? So this is why you don't see here any representation of the environmental flow. Okay, now in the same graph, if you show the upstream and the downstream water level, of course the scale is different with respect to flow. There should be here a second vertical axis, which is not depicted for simplicity. What can we note? First, the upstream water level is constant. Why? Because the barrages are regulated in order to keep the upstream water level at the same level upstream. Downstream, you have the water level which follows the flow duration curve. The water level can be expressed as a function of stream flow. And therefore, you see that the downstream water level is basically a mirror of the flow duration curve. Okay? the difference between upstream and downstream water level is the hydraulic jump. It's what you can use to produce hydropower. The higher the jump, the higher the hydropower that you produce. Hydropower is directly proportional to two things, flow and jump. So when you have more flow, you have more hydropower. When you have more jump, you have more hydropower. But on the other hand, given that the upstream water level is constant, when you have more flow, you have less jump. So if you want to design the power duration curve, you don't have the max power produced for the higher flow because you have a lower jump. So typically you have a max of the power duration curve for the duration of 1,000 cubic meters per second, because you get the most from the combination of flow and jump. The turbine flow, by the way, is constant up to the duration of 60 days or whatever, up to the duration of 1,000 cubic meters per second. And therefore, you have to expect that the power duration curve increases up to that duration because the jump increases while the flow remains constant. And then when you get to the duration of 1,000 cubic meters per second, you have the water flow that starts to decrease. The jump continues to increase, but the combination between the two basically gives rise to what you see on the screen, which is the power duration curve of the hydropower plant of Isola Serafini. Again, this is not something you have to study, but if you're interested in getting the concept, please reflect on this, okay? On my website, there is another figure that I suggest you to look at, which is interactive. It's this is a figure taken from Google Maps, and sorry, you can zoom it. What is this? This is a barrage that is on the Danube River, and I don't remember the location, but if you zoom out, we are about here, in the center of the figure. And if we expand, we get where it's located. It's in Austria, actually, I would say. I don't think it's Czechoslovakia. I would say it's Austria, but it could be somewhere around there. Let's see. It's in Austria. And it's keep in mind that I think it is drawing the boundary between Austria and the Czech Republic, I think, here. So this barrage is used for two purposes: producing hydropower like Isola Serafini, but on the Danube they have many of them. And the second purpose is to sustain the river level in order to allow navigation. The problem of these barrages is that the water quality decreases. They have an impact on water quality because, of course, the velocity of the flow is reduced, and also they are cuts in the ecology of the river. And they are like storing water between them. And therefore, storing water means less flow and means some problems to ensure the ecologic connection. And of course, you know, these big interventions you cannot put a fish ramp there. And the ecologic connection must be established with complicated techniques like fish lifts or complicated features. Anyway, I think it is a good example because here, if you expand, there are two hydropower plants which are, look at my mouse here, for Austria, and here for, I think it is the Czech Republic, but I'm not really sure what is the country that is on the other side. But basically they are two because they serve both countries. They preferred to divide the management of the plant. Another interesting thing is, so this is not a barrage that is done in order to withdraw water. It's just done in order to sustain the river level and producing hydropower. But here you see also the navigation, I don't remember the names, but these are the pools that allows the boats to go up and down to cross the barrage. Okay, this is another example which is interesting to look at. And now we can go back to the PowerPoint presentation. Sorry, let me look at the, I think we have something like 5 minutes, only 5. I thought I was a bit faster, but well, that's fine. And let me just, in 5 minutes, I mean, we can start talking about the second chapter of inductive assessment of water resources. The first chapter is surface water. If you remember, I told you, let's focus on surface water and therefore flow duration curves. And there is a second chapter that we have to open, which is much more complicated in technical terms or in practical terms, let me say, but we will not dedicate much time to it. And it is much more complicated because it refers to groundwater. Groundwater availability is a big question mark. So let me just anticipate one thing, which I think I already mentioned to you. While with rivers, we can get a good estimate, a reasonably good estimate of the volume of water available. So how much water we can take, how much water we can use while preserving the environment, etc. For groundwater, it's not possible. Science cannot provide an answer to the question, how much water is there? What is the volume of water that is there? We can make only some guesses that are by far much rough. The reason is very simple, that in rivers you can measure the flow. For a groundwater body, it is extremely difficult to measure the flow. There is a lot of uncertainty, and there is uncertainty also in the estimate of the volume of water available. You can estimate the volume of the aquifer, but then not all of them is water. So these two question marks combined, the fact that you cannot estimate the volume available and you cannot estimate the flow, make the problem unresolved, still unresolved. Why flow is important? Because it's recharge. So for a river, basically, I'm not counting on the volume. I'm just counting on the flow. It is the recharge. It is, the renewable part of it. Groundwater resources are renewable. Who knows? It depends on the flow. And you cannot really measure the flow reliably. So the question is really open. And so what is the result? That currently we are using groundwater without knowing how much sustainable the use is. So the question of sustainability of groundwater use is an open question. It's fascinating. It's really something fascinating because we are taking from the underground much of our water needs. We are taking a lot of groundwater, but we don't know, we don't have a clue if it is sustainable or not. So don't see it as a reason of concern, as only a problem. It's a problem, but it's also an opportunity, because it's an opportunity for progressing, because it may be that the situation is much better than we think. It may be that the recharge time, the renewable part of it, is much larger of what we assume. Actually, it is unlikely after about 150 years of extensive use of groundwater, it is unlikely that the groundwater will be depleted suddenly. It's not reasonable. I mean, actually, it is reasonable and appropriate to be cautious in the use of groundwater, but there is not really, at least I'm talking at the global level, there is not really a danger of something that is highly unsustainable, but actually it is something that we need to be very careful of. And this is, as I said, an open question. What you see here is a basic scheme, and you see that the groundwater may be subdivided in two parts, unconfined aquifers and confined aquifers. Unconfined means that you have the upper part of the aquifer, of the water body, that is in direct contact with the atmosphere. So you have a free water table, which is in connection with the rivers. It's recharged by the rivers, it's recharged by infiltration, by rainfall, etc. It is also exposed because if you release some pollutants, they reach the groundwater. There is no layer dividing, protecting the unconfined aquifer. In the deep underground, typically you have some confined aquifers. It means that they are not in direct contact with what stays above them, which means that the water is cleaner. It's not directly recharged by the surface, or if it is after a long filtration, a long path of infiltration. This groundwater is therefore more valuable. It's more attractive. On the other hand, given that it's confined, it's very likely that the recharge times are longer, that the flow is lower, and therefore the sustainability of their use may be under threat. And this is the problem. How can we estimate how much water is there? I close this lecture by saying that we have a very primitive way of estimating groundwater, which is wells measuring the level. You drill a well, and then at a certain point you find water and you measure the level. And we will talk about this next time. On Thursday, we lecture again. Next Monday, I think next Monday we have lectures, yes. And next Monday, I will make 1 hour lecture and 2 hours exercises. Questions? Thank you very much. See you on Thursday.
Thank you, Professor.
Thanks.
Thank you, Professor.